So next we'll look at the different ways that we express concentration. So concentration is how we define how much of a solute is dissolved in a solvent. And we have a few different terms that we use, or a few different systems that we use. So we'll talk about percentage. And the percentage can be mass or volume. We'll look at parts per million and parts per billion. These are useful for very, very dilute solutions. We'll talk briefly about mole fractions. And then the two that are most important are molarity, and then less important, but still important, is molality. So we'll start with percentage. And the most common type of percentage we use is what's called mass percent. So mass percent is just literally the mass of the solute over the mass of the entire solution. And then we multiply that by 100. The units that we don't use in this equation don't matter as long as the units match. So we could ask, calculate the mass of 1.52 grams of benzene dissolved in 340.48 grams of toluene. So the mass percent here would be the mass of the solute, which is the benzene. We know that's the solute because that's what's in the smaller quantity. The mass of the solution is all of the solution, so that's the 1.52 grams of benzene plus the 340.48 grams of the solvent. Times 100. And you can also calculate volume percentages. You would do that in exactly the same way. The volume of the solute over the volume of the solution times 100. This is not all that we don't use this very often. Most of the time percentages are mass percents. All right, the next one is ppm, or parts per million. We calculate that as the amount of the solute divided by the amount of the solvent. We use amount of solvent here for the simple reason that because these solutions are so dilute that adding in the amount of solute to the amount of solvent wouldn't really make a difference. Again, unit doesn't matter as long as we use a consistent unit. And then what makes this parts per million is we multiply this by 10 to the 6th. Now we can also do parts per billion. If we're doing parts per billion, then instead of 10 to the 6th, we'd multiply by 10 to the 9th. And you could even do things such as parts per trillion for extremely dilute solutions, and you'd use 10 to the 12th instead. And again, these just get used for very, very dilute solutions. So let's do the following problem. All right, so now we're saying this compound dioxin is considered harmful if it reaches concentrations above 2 parts per billion. So if a lake contains 1 times 10 to the 7th liters of water, has 1 gram of dioxin, has it reached a harmful level? Well, let's see. We can do this problem in one of two ways. And so I'm going to do it both ways. And if you were doing a problem like this on, any sort of test or quiz or homework, you could go either way. So one way is we could figure out what is the current concentration and then compare it to 2 parts per billion. The other way is we could figure out, in order to reach 2 parts per billion, what quantity do we need? But the one thing we notice is the amount of dioxin is in grams, the size of the lake is in liters. So we're going to need to convert one of those. Now, we can't convert the dioxin as a solid. We don't know its density, but water we can. 1 times 10 to the 7 liters is 1 times 10 to the 10th milliliters, which equals 1 times 10 to the 10 grams. So now we can say the lake's current ppb is 1 gram over 1 times 10 to the 10th grams times 10 to the 9th, and that's equal to 0.1 ppb. So we can see at 1 gram we only have 1/10 of a part per billion, and so at this point we can see it's clearly at a safe level. What was the other way we could do it? Well, we could say, given the size of the lake, how much dioxin would it take to reach 2 parts per billion? And so that's what I'm doing here, is I'm saying if we have a lake that has 1 times 10 to the 10 grams of water, what amount of solute would it take to reach 2 parts per billion? Now if we solve for x here, x is equal to 20 grams. So you can see we're quite a ways from the point where we would have to worry about this. And so what about in a larger lake? So what if we were instead talking about Lake Erie? how much dioxin would we need to reach a harmful level? Lake Erie has 480 trillion liters of water. Well, we do the same thing. We would convert our 480 trillion liters. It's 480 times 10 to the 12th liters, which would be 4.8 times 10 to the 14 liters, or 4.8 times 10 to the 17th milliliters, or 4.8 times 10 to the 17 grams. So now we can say 2 parts per billion is equal to X over 4.8 times 10 to the 17 grams of water, that's our solvent, times 10 to the 9th. Solving for X tells us that in order for Lake Erie to reach a harmful level, it would have to contain 960 million grams of dioxin. All right, our third method of calculating concentration is known as mole fractions. And so the mole fraction of any component is just equal to the moles of that component over the total number of moles. All right, from here, just sort of as an easy reference point, I'm going to stop this video, although even if it's a little bit short, and then let the next video be devoted completely to molarity, molality, and some sample calculations.